In this video, I want to talk about the derivative of the natural exponential function e to the x. Or as you can see from the packet, it says that the derivative of e to the x is equal to e to the x. And that can be kind of a strange idea if you've never seen it before. But one of the unique aspects of the natural exponential function e to the x is its derivative is exactly equal to itself. Or basically, if you want to find the slope of the function, it's always equal to the value of that function at that point in time. And it's not an accident that this function has its own derivative. And one of the reasons why it's so important and why it models continuous natural growth is because of the base, the number, what it is. And in class this week, we talked a lot about, okay, what is E? It's approximately 2.72. It's a very special number. It's a limit of a very specific algebraic expression, which can be understood by imagining compound interest by instead of compounding monthly, as we compound more and more frequently. Anyways, we got into all that. But anyways, first of all, why is the derivative of e to the x equal to itself? But let's go ahead and examine this again. And the question, if you ever wanted to know what is the derivative of a function, what we can always start with is the definition of the derivative, which, as we know, is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Basically, the difference quotient gives us the slope of the function between points x and h to the right of x. And as we take the limit as h approaches 0, this will give us the slope as it gets closer and closer together. And all of this is always the definition of the derivative of any mathematical function. So let's go ahead and plug in our function e to the x into the difference quotient and try to examine what will happen. So we'd have f of x plus h. Well, f of x plus h for e to the x would just be e to the x plus h. And if you remember properties of exponents, if we have a sum within an exponential function, that's always equal to the product of, actually, let me write it over here, up kind of like this. It's equal to the product of e to the x with e to the h as a general rule for exponentials, right? Because if you have, say, x squared times x cubed, you add the exponents together. So essentially, if you have this sum within the exponent, you can always break that down as a product. And I'll go ahead and do that. So f of x plus h is equal to e to the x plus h, which is equal to e to the x times e to the h. Then we'd have minus f of x, which is just minus the original function, which would just be e to the x. And all of that would be divided by h. So it's not so bad looking at the difference quotient here. And another thing that you might notice is in the numerator, we have a common factor of e to the x in there, which we could factor out. So we'd have the limit as h approaches 0 of e to the x. And if we factor out e to the x from that, we'd be left with e to the h in the first term, and factoring out e to the x from itself would leave us with minus 1. And all of that would be divided by h. Now, from here, the question might be thinking is, well, how the heck do I find the limit of all of this? But another thing we might notice is that e to the x now has been factored through and is now multiplied by an expression based on h. Well, the limit only cares about h, and that's the variable of concern with the limit. And if you recall, functions with other variables can be pulled through the limit and treated as constant, since that does not vary with h. So this would be equal to e to the x times the limit as h approaches 0 of e to the h minus 1 over h. And again, the question would be, well, what is the limit of e to the h minus 1 over h? And it's a very specific, strange thing. And actually, this very specific algebraic expression has the limit of 1. And again, I would not expect most people to know this, but it's a very famous generalization limit, which was studied a lot by Euler and other mathematicians of the time. And the reason why, basically, it pertains to dealing with derivatives of exponential functions. And this sort of algebraic expression comes through a lot when dealing with all exponential functions. And concerning the limit of it, it depends on what the base is. And what mathematicians figured out is that specifically when the base a is equal to that very specific number e, 2.71828, 1828, blah, 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 this limit turns into 1. So very specifically, this is 1 because it's a special case of a generalized limit, which turns out to be the natural log. Again, we're going to circle back to that in Chapter 2, Section 6 in class this or next week, whenever we get to it. But anyways, it ends up being 1. And also, if you're like, well, how the heck would I know that? Remember, we can always solve limits graphically, numerically, algebraically. Algebraically, this one's a little tricky, and we're not going to do it that way. But let's just go to the numerical approach. Because if I want to know, well, what's the limit as h approaches 0, I could try plugging in numbers close to 0 to see. Like, what if I plug in 0.1 or 0.01? So let's just check it out. If we did e to the 0.1, and then I'm going to go ahead and put parentheses around this for my fraction, minus 1, and then divide it by 0.1. Basically, I'm just substituting in 0.1 for h, which would leave me with this. And what we'd get is 1.05. So again, from just plugging in 0.1, we don't really know very much information. But let's say I get closer and closer to 0, like try 0.01 instead. Notice what I get is 1.005. Or let's say I go down to 1,000th or a millionth or whatever, get smaller and smaller. Again, if I want to know the limit as h approaches 0, I could numerically plug in values getting closer and closer to 0 in for h as a way of estimating or checking what it might be. So let's try 0.0001, and notice it's getting closer and closer to 1. And again, this would be the right-hand limit. I might as well check the left-handed limit as well. Let's say if we were to plug in negative 0.001, but due to the symmetry of exponentials and anyways, it will be the same on both sides, but we can go ahead and verify. Notice on the left-hand side, it's 0.999, aka getting closer and closer to 1. Both the left-hand and right-hand limit are in agreement, so the general limit as h approaches 0 of this algebraic expression, e to the h minus 1, all divided by h, is just equal to 1. So again, a lot of times we might write it like this. That's all evaluates to 1. And long story short, what I end up with is e to the x times 1, which is, of course, e to the x. And in summation, we can figure out, well, what is the derivative of e to the x? It is simply itself. And again, if you were to change the base of this, this limit is not 1. The only time it is 1 is specifically for e, which is how a lot of calculus textbooks define what the number e is. So in the next video, we'll use this fact to solve a bunch more algebraic derivatives, and this will be the type of thing that will appear in your homework quite a bit. But I think it's kind of important to understand, well, why is the derivative of e to the x itself? Again, it is because it is. It's a very special number, and one of the reasons it's so special is because of this reason.